everybody. This is Suvarchala, working as an associate professor, the Department of Computer Science and Engineering. In this video, I would like to explain the traversal techniques for a nonlinear data structure graph, and also analyze based upon the representation of graph how the analysis is going to be varied. So this is related to graphs. So just we'll revise basics of graphs, which most of us are aware based on data structures, representation of graphs, and also graph traversal techniques. Two techniques are there, BFT and DFT. Of course, for searching an element also we have to use these traversal techniques. So that's why these are also termed as BFS and DFS if those are algorithms are used for searching technique. And also analysis of these techniques, how the time complexity and space complexity will be considered for these two techniques actually. Graph is a nonlinear data structure and multiple applications are there in our real-time scenario. A graph consists of mathematical definition, two sets. One is two finite sets. One set represents non-empty set of vertices and a finite and possibly sometimes an empty set of edges. So a graph without edges having a single or multiple vertices without having any connections, then partitions are there. We can say it is also a graph. So a graph is represented as a G of V comma E, where V is a set of vertices and E is the set of edges in general. These graphs are categorized as an undirected graph and directed graph. If the edges are having direction, that means from which node to which node is going to be specified properly, then we will consider the respective graph is a directed graph. In such cases, the edge V1, V0 is not equal to V0 to V1. In case of undirected graph, the direction is not specified. The path can be traversal, can be from source vertex to destination vertex or destination vertex to source vertex. That is V1, V0 is equal to V0, V1. If V1, V0 are two vertices between which an edge exists actually. So directed graph is going to be represented as a pair of sets V and E, where V is a set of vertices and E is a set of edges which are represented in ordered pair. So ordered pair means the order of the vertices also matters in order. Vertices are also often called as nodes in normal programming terminology, and the elements of E are called edges or directed edges or arcs also, need not be lines. So for a directed edge, EW, which is in E, the set of edges, and V is its tail and W is its head. VW is represented in the diagrams as V arrow mark W, V to W in other words. Or simply form, we will write it as a VW means automatically the edge starts from V and ends at W. In case of undirected graph, set of vertices, here it is not ordered pair, unordered pair of distinct elements of V. And here also vertices can be called as nodes and the elements of edges are from V to W and W to V. Both are one and the same. So VW or UWV because VW is said to be incident upon the vertices V and W also. So what is weighted graph actually? So weighted graph means each edge is having some weight or some value, then we will call the respective graph is a weighted graph. So a weighted graph is represented as a top, instead of having a pair here, we are going to represent having three arguments V, E, W. V is set of vertices, E is set of edges, and W is the set of weights. So W is a function from E2 into R actually. So the real elements here, any the real values will be there. It may be integers or rationals or whatever it may be. So for an edge, W of A is called weight of the edge A actually. So in the following graph, it is represented or on each edge some value was represented. That value is going to be considered as the weight of the respective edge. Between A and B, 3.5. The weight of edge AB is 3.5. It is undirected graph. Of course, the weights are there in case of directed graph. And for each edge, A to B as well as B to A, if exists, the weights are maybe different also. So what is a path and what is a cycle? A path is a list of vertices V1, V2, V3, etc. Vn such that each adjacent vertices, that is Va and Vi plus, are connected with an edge. That means they belongs to edge. For all 0 less than or equal to I less than or equal to n. A path, a cycle means cycle is a path in which the last vertex is connected to the first vertex. Begins and ends with the same vertex, then we will call it as a cycle. In the following graph, for example, if you observe P is equal to A, B, C, D, E, that means A to B and B to C and B to C and C to D and D to A, B, C, D, E is there. A to B, B to C and C to D and D to E. This is a path. First vertex is A and last vertex is E and both are not the same, then it is a path. For example, if you are going to consider a cycle, let us assume that I may be considered a path A, B, E, D. If you are considering a path this and D to A, this is a cycle. So this is a cycle means here. So the cycle is going to be a path in which C is equal to, we are going to have a path consists of A, B, E, D, A. So if you observe A, B, E, D, A means here, the path is going to be starting from a vertex A. If you observe A to B, B to E, E to D and D to A. So a cycle forms. So path and cycle, sometimes we need a graph may consist of cycle. Through this characteristic only we can distinguish from a tree. Path length and cast. Path length means the number of edges in a path is path length. Path cast means sum of the weights of the respective edges is considered as a path weight. For example, if you are going to consider A, B, C, D, E path previously, A to B is 3.5 and B to C is 2, 5.5 and C to D is 2.5. That is totally we are having 4.5, 5, 8 and 8 up to E. Then you can consider it as a 3. 8 plus 3 is 11 and 11.5. So the path is going to be considered here based upon that means if you are going to consider the path A to C, C to, just observe A to C and C to B and B to F and F to D. Again D to A. So this is the path. How many edges are there? If you observe 1, 2, 3, 4, 5. 5 edges. Starting and ending vertices are same. So it is also a cycle having the length as 5 edges cast. If you consider cast here, we can consider here as a 2 plus, you are going to have 2 plus 2.5 third edge, fourth edge is 3, fifth edge is 2. So 6, 7, 8, 11.5 plus we are going to have. So the respective edges are considered. So path and path length and path cast. Cast sum of the weights of the respective edges. Path means number of the edges included in that particular path. Coming to the next connectivity, undirected graphs are connected if there is a path between any two vertices. Example is given. Directed graphs are strongly connected if there is a path from any one vertex to all other vertices. Directed graph are weakly connected if there is a path between any two vertices ignoring the direction, if the direction is not considered. but only in special cases only this will be considered. A complete graph means has an edge between every pair of vertices. It may be directed or undirected. Each pair of vertices are having an edge, then we can say it is a complete graph. So complete graph is a graph that has the maximum number of edges because each pair of edges are having vertices are having an edge, no? So maximum pair of number of edges will be there. If it is undirected and n into n minus 1, if it is directed, half of the edges will be considered. Because undirected graph, A to B, B to A are same, no? So that's why for a directed graph with a n vertices, the maximum number of edges is equal to n into n minus 1. If it is undirected, by 2 if you say. If you construct the graph here, so it's a directed graph. Both directions are there. So 1, 2, 3, 4. If you are going to consider here, 3, 4, 2 edges are there. And 5, 6, 7, 8, 9, 10, 11, 12. So 4. 4 into 3, 12. 12 edges are there. If it is undirected graph, each edge is going to be undirected, no? So no need to consider as a 2 edges, A to B, B to C, B to A. So that's why by 2 we can consider. Trees are also can be treated as a graph having some special characteristics. There are no cycles. So every tree is a graph with some restrictions. Tree is directed and there are no cycles in tree. So directed and without having a cycle, tree can be considered as a graph can be considered as a tree actually. There is a directed path from root to the every node. These are the 3 special characteristics of tree. So that a graph can be called as a tree if it satisfies these 3. So there are no cycles and there is a directed path from root to the every node. Then we can say it is a tree. For example, if I consider here, so if there is a edge between D and A, then it is not a tree because it forms a cycle, right? So for example, you are considering one more node I. I is not connected. From root, there is no path to I. Then this is also not called as a tree. So these 2 conditions, cycles, no cycles, and a path from root to the every node, then we can call it as a. Now, one more example is there. You consider the first one is undirected graph, second one is a directed graph. So if there is an edge, in case of directed graph from 1 to 2, 2 to 1 can be considered as a different edge. And directed acyclic graphs are directed graphs with no cycles. Directed graph with no cycles. Generally in a program call, graph is a directed acyclic graph. This is an application when we are using various subprograms are there and the subprograms internal call methods we are using, calling the respective subprograms. If you represent all of them as a graph, then we will get a directed acyclic graph. For example, main function may be invoking multiplication, addition and reading also. In other terms, a add is using or internally invoking access. Multiplication is again accessing adding actually. So trees are going to be considered as a subsets of direct acyclic graphs. Directed acyclic graphs are subsets of the graph. That means directed graphs without having any cycles can be considered as a directed acyclic graph. Seems to be having a cycle actually. So, but it is a directed now. So from here. But here to here means back it is not there. So that's why it is a acyclic. There is no cycle in this directed graph. In any program, the invocation of the subprograms, if you represent each subprogram as a node and invocation as a graph line edge, that means from which subprogram, which other subprogram is invoking. So parent subprogram to the subprogram to which it is called a directed line or edge is going to be drawn. Then we will get directed acyclic graphs. So trees are going to be subsets of directed because trees also don't have any cycles. Directed acyclic graphs are also don't have a cycles, but trees are going to be further restricted. Is restriction is there from root to each node must be accessible, and all are superset graph is superset of these things. How to the implementation of graph, that is while using in programming, how the graph is going to be represented. We cannot represent a graph as it is a picture, no. So we need to represent graph, how many vertices are there, how many edges are there, and how these edges are represented. Various techniques are there. We can represent by using array based representation, linked list based representation. Among these, again, arrays are going to be used to represent adjacency matrix, and in case of linked list representation, we will use two techniques, list representation and multi-list representation. Both are possible. Adjacency list representation is also considered. So coming to the array-based implementation, we can represent a one-dimensional array is used to represent all vertices. So for vertices, one array, and a two-dimensional array is used to represent the edges. So adjacency matrix we will call. So two arrays are used to one-dimensional array and one two-dimensional array. If you observe, this is a graph, a normal map like that, if you can consider, and the weights are respective distances between the respective areas, then we can consider these for representation of our graph. So how many nodes are there? 1, 2, 3, 4, 5, 6, 7 nodes are there. So these are how many? You are going to have 7 nodes are there. Starting from 0, most of the programming languages indices start from 0. So 0 to 6. These are the single dimensional, which represents our vertices. So vertices of 0, vertices of 1 represents Austin, vertices of vertex of 0, Atlanta, and 3 Chicago, and 2 Chicago, 3 Dallas, 4 Denver, and 5 Houston, and 6 Washington. And how to represent edges? How many vertices are the matrix of order, that number of vertices by number of vertices. This is known as the adjacency matrix. So array positions are represented 0 to n, 0 to n. If you observe only 6, no? So this is our adjacency matrix. Even the matrix consists of more elements, other things are only initialized with some unknown data. So 6 by 6 matrix enough for us. But when declaring we are using 10 by 10 matrix, it's okay for us. 7 by 7 matrix is enough. So if you observe, this is 0th vertex to 0th vertex to all other vertices, first vertex to all other vertices. We are considering if any edge exists or not. So based upon the previous map, so for example, if you are having Austin to Dallas is there, Austin to Houston is there, that is 200 and 160, and there are no other edges are available. So you will consider here, when we are considering this, Austin is 1. So 1 to, if you observe, only 1 to 0, 1, 2, 3 for third one, and 4, 5. So if you observe from 1 to 3, what is 3? Dallas, and 1 to 5 is 160, Houston. All others are 0. So if weight is there, we are representing them with a respective weight. If no edge is there, we are representing the adjacency matrix as 0. This is one way to represent. So that what happens, this matrices can be read, this matrix values can be used to find out where are the edges and where are the respective weight of the edge also. So if it is linked list representation, even the linked list, one single dimensional array is used to represent vertices. From each vertex, one list is used, whichever the neighbors are there for that particular vertex actually. That is adjacency list. Now, index, each node is represented using 3 parts. One is the index of the adjacent vertex, weight, and pointer to the next vertex. So, for example, Atlanta, if you are going to consider, from Atlanta, what are the vertices are neighboring vertices? Washington, because 600, Washington, from Atlanta, 800, Houston. So, only 2 neighboring vertices are there. So, that's why 2 nodes are there for some list. That is 3 Chicago, you are going to have Dallas, and 5, fifth node is Houston. So both are there, the respective weights. This is the neighboring vertex number, and this is the weight of the respective edge. If an edge is there, neighbor vertex we will go. That is from each vertex, what are the neighboring vertices are there? All of them are represented by using a list. So this is known as linked list representation. So the graph is going to be represented by using adjacency matrix, and a graph is also represented by using a adjacency list also. So if in case of adjacency matrix, if there an edge is there, generally we will represent edge is there 1, if there is no edge 0. If it is a weighted graph, instead of 1, the respective weight is going to be represented, and if there is no edge, 0 will be represented. But sometimes what happens, 0 is also one of the valid values. So that's why instead of using 0, we may use sometimes infinity also if there is no edge. If the self loop is not considered, then self loop is going to be 0 can be represented. So adjacency list also, we can instead of having 3 parts, we can use 2 parts, respective node value, node number, as well as if there is no weight. Undirected graphs are there, just without having weight as one of the term, we can use it. So adjacency list can be used. That means in case of adjacency matrix, what are the values? From is a node number, 2 is also node number, from to 2. The respective position, if weighted graph is there, weight is presented. If no weight, unweighted graphs, 1 is going to be presented. Otherwise, there is no edge means 0. So by using these notations, we can represent graph internally so that we can write some program and implement graphs in our systems actually. Various applications are there, as I explained you, not only in computer science, day-to-day real-time applications also. Whichever networking environment is there, we can represent it as a graph. For town planning, graph. Waterworks department, graph we can consider. And electricity, a graph. It can be represented as a graph. And so on and so forth. Coming to the computer science, your Google Maps represented by graphs. Facebooks, because social network, any social network, vertices are to be considered as users, and friends are going to be considered as edges. Operating system, resource allocation is there. So a computer system and all resources are going to be considered as a process, and resources are considered to be as a vertices. And a process is request or accessing a resource, an edge can be considered. So if any formation of such cycle is there in operating system between resources and vertices, if you are going to consider resources allocation graph is there, then if it graph consists of cycles, it is under deadlock condition. Like that, various graphs are there for us. Now we will enter into our actual the purpose of the graphs traversal. So we can consider these traversal techniques are a graph traversal techniques or a graph search techniques. Both are one and the same almost. A slight variation is there. Search means whenever the element is accessed, we will stop the process, and unsuccessful search is considered as a traversal, in other words. So that's what we'll discuss as a traversal. So for search also, just by adding an additional constraint, it can be converted into respective search techniques also. So graph traversal is a technique used for searching an element or a vertex in the graph also, and a traversal means accessing each and every node once. So the graph traversal is also used to decide the order of the vertices visited in the search process also. So a graph traversal finds the edges to be used in the search process without creating any loop. If loop exists means we are going to consider the same nodes are going to be searched further actually. So that's why by using graph traversal, we will visit all vertices of the graph without getting into the loop or without getting into the cycle form. So there should not be any cycle in our path while using this traversal. Otherwise, there is no ending of the process at all. There are two techniques are there, breadth first traversal and depth first traversal techniques, or in other words, we'll call it as a depth first search traversal and depth first search traversal. So this depth first search traversal is used in topological sorting, scheduling the problem, cycle detection in graphs, solving various puzzles, only one solution such as a maze or a Sudoku, etc., and many other applications involving networks. For example, testing if a graph is a biparty graph or not, like that. Various applications are there which can be solved or which can be answered by using this depth first search traversal. Similarly, breadth first search traversal uses in many applications as a crawlers in search engines for indexing web pages and GPS navigation, shortest path and minimum spanning trees. Also, we can use this breadth first traversal. Unweighted graphs breadth first traversal can provide us minimum spanning tree also, and broadcasting most of the time, peer-to-peer networking. In all these cases, we can use BFTs or BF breadth first search traversals can be considered. So, by using this graphs, traversal technique can be implemented by using either of these two techniques, breadth first traversal techniques or depth first traversal techniques. Any of these implementation, that is implementation of BFT or implementation of DFT also, depth first traversal also, we will use these three requirements. That means we will use an additional variable known as a status. In both cases, BFT as well as DFT. In both cases, we will use an additional variable status. What is this status specifies? So this is the status is an array of n vertices. For each vertex, the status is going to be represented. For example, statuses of I. Status is an array, single dimensional array. Status of I means status of the node I. Status of the node I. What is the possible values of this status? 1, 2, 3. Either of any of these three values. It may be 1 or it may be 2 or it may be 3. So status of ith node. For each node, the status is going to be keeps track so that what is that particular node current status is going to be easily understood by us. In both cases, BFT as well as DFT, this status variable of each node is going to be considered. So what is this status? 1. 1 is ready state. That is the initial state of all nodes will be ready state only. That means they are ready to process. If the status is 2 means it is waiting state. That means it is accessed by the respective technique and it is waiting to get served. And if the status is 3 means it already processed. Processed state means it already processed. If it is a traversal, printing or whatever, it may be processed. That means no need to consider the respective node further. So by using this status variable, we can easily implement the logic to avoid the cycles also. So in addition to this status variable, these traversal techniques uses additional auxiliary space also, memory space. So BFT will use Q is an additional auxiliary data structure to represent intermediate storage of the nodes, and our DFT uses stack. So BFT uses Q as an additional auxiliary temporary storage data structure, and DFT is used to stack as a temporary auxiliary structure to store the node name values intermediately. So we'll discuss how the depth first traversal works. First we will discuss only traversal. If it is a search, you have to stop at every node. You have to, whenever it is processing there, you will check whether the node is having required value or not. If it consists of, you can stop. The traversal process can be stopped there itself. So that's why search is a subset of the traversal. So we will discuss about the traversal only, so that can be used further minor modifications for respective searches also. So how this depth, the term itself indicates. Depth means visits the adjacent unvisited vertex, mark it visited, display it. Display using the traversal. Push it into stack. If no adjacent vertex is found, pop from the vertex from the stack, and it will be pop up all the vertices from the stack which do not have any adjacent vertices. Repeat and step 1 and 2 until the stack is empty. If the stack is empty, there are no vertices further. So this depth first search traversal works of undirected graph uses or proceeds like that. First, it will examine the starting node, whichever the node you can start. Not like in trees from the root only. So that's why we have to start from any node, and the process is continued. So if the next unvisited vertex W adjacent to V is selected, and the depth first search from W is initiated. When a vertex U is reached such that all its adjacent vertices have been visited, we will go back up to the last vertex visited, which has an unvisited vertex W adjacent to it. The search is going to be terminated when no unvisited vertices are available, as well as our stack is also empty. So the algorithm is similar to the ordered traversal of binary tree, and DFT algorithm uses stacks as a temporary storage, and again status is used to tell us the current status of the each node. So this is the normal DFT pseudocode. So initialize all nodes by ready state, that is initially all nodes status is 1 only. Push the starting node A from whichever the node you would like to start, that we will consider as a starting node, into the stack and change its status as a 2. So as long as status is 1, not yet processed at all. It is 2 means it is ready to process. If it is 3 means it is already processed. So repeat the following steps until the stack is empty, that is pop from the node, from the stack, process that particular node and change the status as a 3. Whatever will be the process, let us assume that we will take it as a print now. Push all neighboring nodes of n into the stack, that is which are having status 1, those are going to be pushed into stack so that the status is going to be changed to 2. This process is repeated until the stack is empty. Now this is the normal algorithmic notation pseudocode. We can DFT algorithm. If you observe here, visited of V is equal to 1. So this is going to be initially all of them are going to be 1. Visited is a global array. So current vertex we are visiting. So that's why visited of V is equal to 1 initially. And we are checking all adjacents of the V, and we are checking the status of the respective vertex. If it is equal to 0, then we are calling it recursively. Otherwise, we are adding to the queue, and instead of W, we are making it as a 1. So this process is a recursive calling of the respective vertex. So if you consider the process of example here, depth first search. So we will take an example and we will work with the respective depth first search, how it works. So this is a graph. This is a stack, given stack. We are starting from A. So we are changing the color A. That means changes the status as initially 1. All of them are having 1. And when we are starting means we are pushing into stack now. We are making it as a 2. And all adjacents of the A are considered. So adjacents of the K are, we are pushing into stack and we are processing also. So output is A. B is adjacent. It is converted into 2 and pushed into stack. Outputted B. another adjacent. Now we are considering it as the adjacent of B is D, depth first, that is pushed. Adjacent of D is, you can consider either E or F can be considered depending upon the structure you are using. Here we are considering E. So E is pushed into stack. Adjacent of E is going to be F. F is pushed into stack. Adjacent of F, we have D and E, but D and E are already status is going to be 2 which are pushed. So we will pop from that particular stack. So F is removed. That means moved. Pop from the again stack. Again we will consider adjacent of E. E is popped out. Adjacent of E is C. C is pushed into stack. Afterwards we keeping on popping from the stack which are already processed. So what is our DFT traversal starting from A? If you observe A, B, D, E, C and we stopped, we will go back one. Adjacent of E is going to be C. C is going to be processed. After that it's going to be stopped because all of them are having what is indexing as 2. So if you consider adjacency list, you can consider either adjacency matrix or adjacency list. For example, if you are going to consider adjacency list, let us assume that this is the graph and from A, F, C, B are adjacency list. If you consider B, adjacency list are again A, C and B. So A, C and G. So A, C, G. This is adjacency list. While representing this adjacency list, there is no any rule actually. I can represent FCB or I can represent BCF or I can represent BC, CBF, etc. Any way you can use. So depending upon that, the order is going to be changed. No need to worry about that. So FCB, ACG, this is adjacency list. That means adjacency list means for each node, what are the adjacent nodes are there, we represented them. For convenience sake, in some applications, we may represent these adjacency list in a alphabetical order also. It's up to that. No problem to us. So when we consider this is graph and adjacency matrix, and also we will represent this position of the stack also, then we can understand a better way. So this is the graph. I am starting from A. What are the adjacent? What is this? Adjacent vertices are going to be. Initially you observe all vertices are having the stack status as 1. So 1, I am starting from A. A is pushed into stack. So this is the stack position. While pushed, stack position is considered as the respective element status is going to be changed to the 2. Now, so we have to pop out from stack and process. So I process the node adjacent are BCF. Those are pushed into stack and we process the node 2. Status of node is 3 and the adjacent nodes of A are pushed into stack BCF. So you observe this B, C, F. These are changed to 2. Currently stack. Then what we supposed to consider? We have to pop out from the stack and F is popped out, outputted. So F status is changed 3 and all what adjacency values of the F are considered. So all adjacency values of F are A and C and D are there. But status of A is 3. So no need to consider further. You observe wherever A comes, A is already processed. No need to consider. And what are the other two? C and B. So you observe C is already 2. It is there in the push into the stack. So we have to check, consider only D. D will be pushed into stack by changing its status as 2. So this process is continued till we are going to get the respective values actually. So when we are considering this process, we are going to consider the respective graph representation and we will use the respective process. So by using this algorithm, and we can use the depth first traversal. So I'll consider here one more example. So this process is continued in the previous case when we are representing the process. So this is going to be considered as a 2 changing, and whenever we are popping and we are considering its adjacent nodes, we are making it as a 3. So this process is continued until stack is empty, and whenever we are pushing into the stack, we are checking what is the status of the current node. If the current node status is 1, then only we are pushing. If it is 2 or 3, we need not consider. So this is the way to check the respective cycles exist or not. We are getting A, F, D, J, K, G, E, C, B. Of course, don't worry much if sometimes this order is going to be a little bit change may occur depending upon the adjacency lists are maintained for the respective graph actually. Right? So we will use discuss the respective process of traversal technique by using the stack. Let us assume that how it works just you observe, and we are starting inserted V0, and then we inserted V3, then we inserted V2, then that means V0 adjacent to V0 is going to be V3, adjacent to V0 is going to be our V1, and V1 to V3, and like this we are going on pushing actually. So order of the visiting vertices are going to be, it may be V0, V1, V2, V0, V1, then we may consider it as a V2, V3, or V0, V3, V2, then we can be V1, or V0, V2, V3, V1. That means the order need not be the same, remember all of us. Why? Because in which way the data was pushed into stack, that is vertices are pushed into the stack, in that order only the popping will be considered. That means the pushing is going to be done depending upon the adjacency list order representation. So that's why no need to worry much about the order in which we are getting. Similarly, breadth first traversal is going to be there. Breadth first traversal means it may be considered as a similar to our level by level. Visit the adjacent unvisited vertex, mark it as visited, display it, insert it into queue, and no adjacent vertices are going to be found. Remove the first vertex from the queue, then repeat step 1 and 2 until the queue is going to be empty. That means we are, while inserting into the queue itself, we are considering it as a processing also. When we are removing them, then we are going to pointing into the process complete. Here we are using instead of stack, that is last in first out. Here we are using first in last out. So this breadth first traversal algorithm begins at the starting node, examine the starting node, then examine all its neighbors, then each neighbors are going to be considered. So the status tells initially the status is 1. When put starting node A as a insert into queue and change its status as a 2, repeat the following steps until the queue is empty. Remove front of element front and vertex n from the queue, process n, and change the status of n to the 3. Add this rare to the queue, all neighbors of n, and when it is ready status is there. When it are inserting into queue, it will become as a 2. This process is continued until the queue is empty. For example, if you are considering BFS of V, U is equal to V, visited of V is 1. Repeat for all vertices of W adjacent U, and if it is visited, then it is going to be, status is going to be changed. Then the process is continued. Delete from the queue and complete the process. So when we are considering this adjacent vertex here, vertices here, and we will consider one example for BFT traversal also. So visited initially all are 0, not visited no. So when it is front end, rear end are minus, and we starting from A. A is going to be inserted. So A is inserted means front and rear are going to be same initially. Print the node pointed by the front and insert the unvisited neighbors of the node into front. Remove the element from the front. So that means A is visited now. So BC are inserted into our queue and A is already visited. B1, B and C are also inserted into queue means visited. Then we are deleting from queue, that is B is deleted. All neighbors of B means D, E are inserted, change their status. Then we deleted from C and C is going to be deleted. All C at neighbors, C neighbors are only A and E. Already they are listed. So that's why. That means those are not going to be changed. C is printed, delete from Q, D is deleted, and neighbors of D are B, F, E. B, F, E are already visited. That means the status was changed already to 1, B, F, E, all of them. So F is going to be inserted here. Then delete from no unvisited neighbors are there. So remove the element from the front. E is taken. Neighbors of E are all unvisited. F is taken. Neighbors of F is also considered by C and already which is visited. So like this, the division when we are doing this, visiting of the process is considered by visited status. We can consider the respective specification of the example, whether it is visited or not visited. Based upon that, two queues are represented. We can process the nodes. For example, if you are considering the same graph, you observe initially all of them are 1. When it is inserted into queue, then it is changed to 2. And we are considering breadth first now, all its neighbors. All its neighbors we are considering, and all neighbors are inserted in, and we are deleting from the front end each first neighbor, neighbors of first neighbor, neighbors of first neighbor. When we are deleting from queue, we are changing its status as we are processing and changing the status as 3, and all its neighbors are inserted. So such a way, if we are going to consider, we will get A, F, C, B, D, E, G, J. So let us assume that we are going to consider as a graph. This is the graph we consider. Adjacency list we are considering. So that means from A, all its FCB, from F, all its adjacent vertices. That means only D. Like that, this is going to be continued. So the steps involved in the breadth first traversal, based upon the previous example we are considering. Every time it is considering all adjacency list. All adjacent nodes are going to be inserted, provided the respective status is equal to be 1. If it is 2 or 3, we will ignore it. So based upon this process, we can get the status of the process nodes is going to be considered. So if you observe the previous example, for example, V0, V3, V1, V1, V2. Adjacent means first V3, V4, V1 are going to be, for V0 is inserted, V3, V1, V4 are its adjacent. Then V2 is adjacent of the V3. So the order of the visiting nodes can be V0, V1, V4, V, because V0, V3, V1, V4, or V1, V4, V3, V2, or anything can be considered. So the breadth first traversal techniques are there, depth first traversal techniques are there. Each of them are going to be having its own advantages and disadvantages. And these traversal techniques are used specifically for a particular application. But if we observe here, the time complexity of these breadth first traversal or a depth first traversal are same as the height of the tree, you can consider, in other words. That means here, whenever we are using, it depends upon the number of edges and number of the nodes only. So the maximum time complexity or space complexity of our graph with n vertices and e edges are time complexity is theta of n plus e, that is number of nodes plus number of edges, whereas space is going to be number of nodes. But remember, whenever we are using this time complexity, it depends upon the way the data is or a graph is represented. If you are using this adjacency list, then the time complexity is number of nodes plus number of edges. But if you are representing by using an adjacency matrix, then what happens? We have to traverse the matrix, no? So the time complexity is order of n square. It is n plus e, this is order of n square. Because the matrix is having n by n matrix, no? So we are going to order of n square. The processing is going to be taken a nesting of the loops, row and column, no? So the nesting of the loops is going to be considered. The maximum time complexity will be order of n square. Space is same as our number of nodes only. So if you observe here, depending upon the way we are representing our graph internally, so if the graph is represented by using adjacency list, the maximum time taken, burst time taken by the graph traversal technique, either BFT or DFT, is order of n plus e. Whereas if it is adjacency list, a matrix form is there, no? So a row and column inner loop, nesting of the loop must be used by us. So that's why order of n square. But in both cases, auxiliary space is going to be either stack or a queue, whatever it may be. The size of the respective auxiliary space, additional space, is order of n only. So that's why the graph algorithms the time complexity depends upon how the graph is internally implemented or represented. So based upon that, the time complexity varies. Okay. So by using this graph traversal techniques, we can implement any of the real-time application which can be represented as a graph in which we can access. Specifically for shortest path algorithms or finding a distance between a pair of places in any map which can be represented as a graph, or the cost of establishing a minimum waterworks network. All these are applications of our graphs. Traversal is required actually. Thanks for watching. Depending upon that particular graph representation, the time analysis can be done by us. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.